The memory hierarchy. Storage technology. Different storage technologies have widely different access times. Faster technologies cost more per byte than slower ones and have less capacity. The gap between CPU and main memory speed is widening. Computer software. Well-written programs tend to exhibit good locality. In one of the happier coincidences of computing, these fundamental properties of hardware and software complement each other beautifully. They're complementary. Nature suggests an approach for organizing memory systems, known as the memory hierarchy, that is used in all modern computer systems. Figure 6.23 shows a typical memory hierarchy. In general, the storage devices get slower, cheaper, and larger as we move from higher to lower levels. At the highest level, L0, are a small number of fast CPU registers that the CPU can access in a single clock cycle. Next are one or more small to moderate-sized SRAM-based cache memories that can be accessed in a few CPU clock. Caching in the memory hierarchy. In general, a cache, pronounced cache, is a small, fast storage device that acts as a staging area for the data objects stored in a larger, slower device. The process of using a cache is known as caching, pronounced caching. The central idea of a memory hierarchy is that for each K, the faster and smaller storage device at level K serves as a cache for the larger and slower storage device at level K plus 1. In other words, each level in the hierarchy caches data objects from the next lower level. For example, the local disk serves as a cache for files, such as web pages, retrieved from remote disks over the network. The main memory serves as a cache for data on the local disks, and so on, until we get to the smallest cache of all, the set of CPU registers. Cache hits. When a program needs a particular data object D from level K plus 1, it first looks for D in one of the blocks currently stored at level K. If D happens to be cached at level K, then we have what is called a cache hit. The program reads D directly from level K, which by the nature of the memory hierarchy is faster than reading D from level K plus 1. For example, a program with good temporal locality might read a data object cache misses. If, on the other hand, the data object D is not cached at level K, then we have what is called a cache miss. When there is a miss, the cache at level K fetches the block containing D from the cache at level K plus 1, possibly overwriting an existing block. If the level K cache is already full, this process of overwriting an existing block is known as replacing or evicting the block. The block that is evicted is sometimes referred to as a victim block. The decision about which block to replace is governed by the cache's replacement policy. For example, a cache with a random replacement policy would choose a random victim block. A cache with a least recently used LRU replacement policy would choose the block that was last accessed the furthest in the path. Kinds of cache misses. It is sometimes helpful to distinguish between different kinds of cache misses. If the cache at level K is empty, then any access of any data object will miss. An empty cache is sometimes referred to as a cold cache, and misses of this kind are called compulsory misses or cold misses. Cold misses are important because they are often transient events that might not occur in steady state, after the cache has been warmed up by repeated memory accesses. Whenever there is a miss, the cache at level K must implement some placement policy that determines where to place the block it has retrieved from level K plus 1. The most flexible placement policy is to allow any block from level K plus 1 to be stored in any block at level K. For caches high in the memory hierarchy, close to the CPU, that are implemented in hardware and where speed is at a premium, this policy is usually too expensive to implement because randomly